Recall that we started talking about a second order equation. So it might be useful to find the Laplace transform of a second derivative. Turns out that that's actually quite easy to do. And I'm just going to kind of point in the direction. I'm not going to completely derive the formula. But if we let u equal e to the negative st dv equal to f double prime of t dt, you can fill in the details. The du is negative s e to the negative st, and the v will just be f prime of t. So we're going to get f prime of t e to the negative st evaluated between 0 and infinity plus s times the integral from 0 to infinity of f prime of t e to the negative st dt. The steps are identical to those we used in I think the last clip in finding the Laplace transform of f prime, except that now we're finding the transform of f double prime, whose integral is just f prime. This, evaluated at 0, is going to give us just f prime of 0, and that's the lower limit, so that's negative. The upper limit, as long as t's t's greater than s, is going to approach 0. And I don't think I said that right, but you know what I mean. Okay, plus s times this integral that's just negative f prime of 0 plus the Laplace transform of f prime of t. And we've already found the Laplace transform of f prime of t. There's a factor s here, so that I shouldn't really write this step out. I should leave it to you, but it's s times negative f of 0, and then it's going to be plus s times the Laplace transform of f of t. And that then ends up equaling s squared times the Laplace transform of f of t minus f prime of 0, just trying to decide what order to write those in, minus s times f of 0. So if we have a second order equation where we know, where we have initial conditions on the function and its derivative, of course we'd be applying this to y. So if we have the equation, let's say y double prime, well, let's just write it out. My double prime plus gamma y prime plus ky equals some function. My notation's a little unfortunate. This f is not this f. This f is just a dummy function to which we want to apply integration by parts. This f is your forcing function, different function here. Make sure we're clear on that. This is a different f. Of course, we're going to Laplace transform this f, but that's just a simple step. So we have what? M times y double prime. If we want to Laplace transform that, well, we get m times the Laplace transform of y double prime plus gamma times the Laplace transform of y prime plus k times the Laplace transform of y equals the Laplace transform of f of t. The Laplace transform of y double prime by this formula, if we use y instead of f, is just s squared times the Laplace transform of y minus y prime of 0 minus s times y of 0. So we've got the Laplace transform of this. Really nothing to it with a little bit of practice. It's the inverse transform that can be a little bit hairy. And then we've got gamma times the Laplace transform of y prime. And the Laplace transform of y is just s times the Laplace transform, didn't say it right, Laplace transform of y prime is s times the Laplace transform of y minus y of 0. And then we have k times the Laplace transform of y, and that equals the Laplace transform of f of t. I hadn't really intended to jump all the way to this function. We're getting to what we call a system transfer function, but it's as good an illustration as any at this point, so let's go ahead and work out the rest of this. And the rest of it's just algebra. As in a previous example, we're trying to solve for the Laplace transform of y. Assuming we know our forcing function f of t and can Laplace transform that function, we should be able to solve this for L of y. And of course, also knowing our initial conditions on y prime and y. I'm going to write out a little bit of this on the next page. The algebra is very simple. I'm just going to distribute through these parentheses here and then separate off the terms with the L of y's on the left-hand side, put everything else on the right-hand side. Okay, as advertised, I've written this function, this equation, and I'll just point a little bit. I've got an L of y here. It has ms squared as its, here's our L of y, ms squared is a factor, gamma s is a factor of L of y, and k is a factor of L of y. On the right-hand side, I'm going to put, of course, L of f of t, which is already on the right-hand side. And then I'm going to correct a couple of signs. Going to add the m y prime of 0 and the ms y of 0 and the gamma y of 0. So that my equation becomes this. Now, if we're actually testing a spring mass dashpot system, I said it right, I had to hesitate, but if we're actually trying to determine the mass, the drag force constant and the restoring force constant of such a system, we would typically test the system hanging at equilibrium or sitting at equilibrium with zero initial velocity. There's really no reason to complicate it with anything but zeros on y of 0 and y prime of 0, our initial position and velocity. So if those are both 0, these terms drop off. If we divide through by the ms prime plus gamma s plus k, we get Laplace transform of y equals the Laplace transform of s over ms squared plus gamma s plus k. And if we know the Laplace transform of our forcing function, and our forcing function is something we can certainly control, we can decide what force to apply and apply it, whatever function, a sine function, a cosine function, a step function, and step functions are very common in this kind of application, or some kind of a square wave function. Whatever our function is here, we can Laplace transform it. And the harder thing is to observe our output function, our y function, but if we can observe the y function and Laplace transform it, then what we see is that 1 over ms squared plus gamma s plus k is going to equal Laplace transform of y divided by the Laplace transform of f. And on such a system, typically this quotient is going to give us a reciprocal of a quadratic function, Or if we want, we can take the reciprocal of this and do L of f over L of y. So we've kind of come full circle already with our original question. And in the process, we've seen how we can use Laplace transforms to solve differential equations. Now we're going to go ahead and fill in a few of the details starting in the next clip.